morning everyone. I'm from MD, and the topic of my presentation is quantum corrections to Hawking temperature of regional Nordstrom black holes surrounded by fringes. And this is the outline of my presentation. And first, a brief introduction on Hawking radiation and fringes. In 1972 and 1974, Bekenstein and Stephen Hawking they found a link between black holes and thermodynamics. In 1972, Bekenstein proposed that the entropy of black hole is finite and it is proportional to the area of the event horizon. And in 1974, Stephen Hawking used the quantum field theory in curved space-time and proposed that the black holes behave as thermodynamic objects which emit thermal radiation with a characteristic temperature, and this radiation is known as the Hawking radiation, which is due to the vacuum fluctuation near event horizon. And quintessence, it is one of the candidates for dark energy, and it is a scalar field which is characterized by the equation of the state. Pressure equals the state parameter times the energy density, and the state parameter is in the range -1 to -1/3. So Hawking radiation have been studied as a tunneling process where the emitted particles or the radiation tunnel across the event horizon of the black hole, which acts as a barrier, and this process helps in understanding the underlying physical process of the Hawking radiation. And the quantum tunneling methods we have are the geodesic method by Parikh and Wilczek and Krauss, and another is the Hamilton, Jacobi and Sass by Haben, which is an extension of the work by Padmanabhan. In general, this tunneling methods involve calculating the imaginary part of the action of the emitted particles, which in turn is related to the Boltzmann factor, and from that we calculate the corrected Hawking temperature. And coming to the topic, there is no Nordstrom black hole surrounded by fringes. So Kislev, he first solved the Einstein field equation for static spherically symmetric solution of black holes surrounded by fringes, and from this we deduce the line element for the regional Nordstrom black hole surrounded by fringes, which is given by this equation. And the FR and the GR is this, and the last term is due to the presence of the fringes. The M and Q are the mass and the charge of the black hole, and from here we obtain the inner and the outer and the inner horizons, which are given by R plus R minus. And considering the quantum gravity effects, we use the generalized uncertainty principle, and the uncertainty principle gets modified to this form. And using this, we get the generalized Gordon equation, which is also modified to this equation for the scalar field psi. Here we assume an ansatz of this form for the scalar field, and substituting this psi into the Klein-Gordon equation, we solve the equation of motion of the emitted particle, which is the Hamilton-Jacobi equation, which is given by this equation. And from here, the solution exists in the form, the solution of the action exists in this form. And by solving this, we get a quartic equation. And by solving the quartic equation, we get two meaningful solutions of the radial part of the action, which is W plus and minus. The plus indicates the outgoing wave and minus indicates the incoming waves. So we'll be considering the outgoing waves. The result for the outgoing waves, W plus, which is the imaginary part of the action of the emitted particles. And by using the By using the solution for the outgoing weight in WKV approximation, we find the tunneling rate, which is given by the exponential of -2 imaginary part of the action, and by comparing this to the Boltzmann factor, we calculate the corrected Hawking temperature. And for now we are considering the state parameter to be of -1/3, and for this the corrected Hawking temperature comes out to be this, where T0 is the original Hawking temperature of the Reisner-Nordstrom black hole surrounded by quintences. And in conclusion, so we have determined the Hawking temperature of Reisner-Nordstrom black hole surrounded by quintences in the presence of quantum gravity effects. And in the absence of quantum gravity effects, the original Hawking temperature is recovered. And in the absence of quintences, the original Hawking temperature of the Reisner-Nordstrom black hole is also recovered. And from what we can draw from these results are, so in the presence of quantum gravity effects and quintences, the rise in Hawking temperature is slowed down, and the corrected Hawking temperature depends not only on the properties of the black hole, but also on the properties of the particles emitted. And the corrected Hawking temperature, it also depends on the quintences parameter. And these are the references that I've used, and thank you.
Okay, thank you for being in time. It's now open for discussion. If any question?
What is the motivation that you take the quintessence surrounding the black hole?
Yeah, sir. In this, we are considering quintences as a scalar field model to describe the dark energy.
You are taking specific dark energy models, or it is model independent? Right now, your method is model independent.
Sir, I have just.
I can see equation of state, but apart from that, there is no information of the quintessence.
Quintences, sir. There is this modification in this one line element of the Reisner-Nordstrom black hole.
True. There the equation of state is present.
Yeah.
In the last term.
The last one.
Okay, is there any more questions? Yes, one more.
So, like this is the that one that FR function. So you said that that Reisner-Nordstrom metric is modified in the context of quintessence model. So, like we know that Reisner-Nordstrom Q is an electric charge, right? But if you modify using in the context of quintessence, what actually Q represents here? I mean, like, is it an electric charge or is it something modified?
Yes, it is a charge of the black hole.
Charge of the black hole. But in general, I mean, like, black holes are, I mean, they're neutral, right?
I don't think so. I think there are different types of black holes, charged and uncharged.
We can take.
I think astrophysical black holes are charged.
Yeah.
So, any typical value to this charge?
No.
No, any typical. Do you know any typical value?
No.
Okay, is there any more questions?
That can be inferred from the shadow measurement that is one of these. Okay.
So, lab value. I am interested in the
RAB value, typical value.
Sir, right now I'm not considering.
Well, if there is no naked singularity, that has to be less than m square. That is
Okay. Then
clear from the equation.
This is only theoretical.
It is only theoretical.
Okay, if there is no more questions, then let us thank the speaker once more for nice presentation. Now, the next speaker is Monu Singh. Okay. Title is Dissipative Accretion Flow around black holes with viscosity prescription as a function of radial distance.
Hi everyone, I am Manu Singh. So I am a research scholar at IIT Guwahati, working with Professor Shantanu Das. So in 3 days you have heard a lot about accretion disks, accretion flows, and black holes. So here I'm going to present one more aspect of the accretion flows, so which is viscosity. Okay, so let's jump in. So this is the outline. So yeah, first thing first. So what viscosity actually does? So as we know, so what viscosity does is it transports the momentum. So let's consider a case here. Let's say we have a system where we have a black hole here sitting here, and we have a secondary source. So if you want matter to fall from here to here, you need to lose the angular momentum. Then only matter can fall into the black hole. So first thing is this, that viscosity transports the angular momentum outward. Another thing is when there is a fluid and one layer moving over another, the matter will get heat up. So this is the two role which is played by the viscosity. One is to heat the fluid, and another is to transport the angular momentum. So yes, so here we are talking about the accretion flows. So how do we define viscosity here? So here, so this journey of understanding the viscous properties of the accretion disk given by these gentlemen, Sakura and Suniev. So we are just on the dimensional basis. They parameterize this viscous stress in terms of the pressure. And this alpha which is sitting there is the parameter which dictates the amount of viscosity. Okay, but and one more thing, this prescription was based on the idea of the turbulent viscosity. But what seeds this turbulence was not clear up to these gentlemen, Barbas and Holly, which says if there is a differential rotation and magnetic field is there, so magnetic field act as a tension and or like a rubber band. Okay, and there is a differential rotation is there. So what happens? Let's say we have a central mass here, and we have a two blob of mass. One is this one, inner one, and outer one. And since there is a differential rotation, the inner one is going with higher angular velocity than the outer one. So what happens? This will try to go inward. Okay, since there is a little bit perturbation, so this wants to go inward, but there is a rubber band which try to pull it. So when it pull it back, so by that mechanism it gains the momentum and it loses the momentum. So this will go further in, this will go further outward. So this way the angular momentum is transported to the flow. So this is magnetic rotation instability. And another thing is when this Sakura Suniev considered this prescription, here the advection was neglected in the radial direction. So then these gentlemen came up and they said if there is a advection, then flow might be supersonic, and in that case there is an importance of the ram pressure, where this is the density, vertically average density, and this is the flow velocity. So this is how how we define the viscosity. So far so good. And this alpha here is the dimensionless parameter. Okay, so up to which this alpha was considered to be a constant. Okay, but later on, when these simulation studies started, that computer gains more importance, people started doing simulations. And let's see what happens. So then when people starting simulation, they find out in their studies the alpha which was considered to be a constant needs to be a constant, but can vary temporally as well as spatially. And later on, it was also shown by other researchers like these recently, Bomik et al., that the outbursts in some black hole sources may be triggered by the local change in the viscosity. Another study which came up early, the Zhu et al. In their GRMSD simulation, which is general relativistics, magnetohydrodynamics, which also showed that alpha might vary as r to the power 0.5. So here our main goal is to understand, if we consider this alpha to be a non-constant, then how the dynamics of the accretion flow dictates. Okay, so as I said, these people showed alpha might vary like this. So for a general case, we choose alpha to be a form of light which varies r to the power theta, where rg, since this has to be dimensionless, so we just multiply it with this unit of length, which is Rg, GnBH by c square. So instead of one parameter, now we have a two parameter viscosity. One is alpha naught, another one is theta. So let's see how thing goes. So yeah, all of you have seen these equations. So first one is this first one and 3 is the nothing but the nearest equations. One is the radial direction, another one is the azimuthal direction, where v is the flow velocity, r is the radial distance, h is the enthalpy, rho is the density, p is the pressure, and phi is the effective potential. This is the gravitational potential which dictates the space-time. And here we have considered the pseudo-curve black holes. And this second one is the conservation equation, which comes from the continuity equation. And this is the azimuthal equation. So here where the viscosity plays the role. So this is lambda is the angular momentum of the flow, and WR phi is the viscous stress. So here all the plane will be governed by here. So let's moving on. So we have an entropy generation equation, which is nothing but the second law of thermodynamics. And here this is the cooling in the system. So if because matter is getting heat up, so by suitable consideration of cooling, flow might radiate that heating. Okay, so this is we have considered here the synchrotron cooling, which is of a form this form, and here we have this one is the viscosity, and here this is the space time, which is pseudo curve potential, which we have considered here, and this is the unit system we works in. So yeah, and this is the equation of state, as my colleague explained. This is the equation of state where rho is density, tau is given by this, and otherwise these are the numbers which depends on the mass of the electrons and the protons in the blob of a mass, and theta is this dimensionless temperature. And since it is a relativistic equation of state, because as explained earlier also, flow is at the outer edge is cold as compared to the inner edge. So we have to also take care of the temperature, thermodynamic relativistic or non-relativistic, which is governed by this polytropic index, and this is the adiabatic index, and this is how we define the sound speed. So yes, if we juggle all these equations, so we get these two equations. First one is this equation. This is the this dimensional temperature, and this is the momentum equation. So primarily we have to solve these three equations to get the equation solution. Okay, so how do we do it? So yes, to do this, we fix our parameters at the outer edge here, or injection radius. So we start our flow from here, somewhere here, to be RH to be 1500 with these numbers, lambda this and h is this for the non-rotating black hole. And here this m dot is the parameter which controls the cooling. More m dot, more cooling in the system. Okay, so as you can see, interestingly, as we increase the theta, this will increase the viscosity, which will remove the more angular momentum. Okay, so because this in the equation there is a centrifugal barrier and the gravity, so there is always competition between these two. So when you remove the angular momentum, the flow loses the centrifugal barrier and this velocity shoot up. Okay, interestingly, you see here flow was passing through the inner critical point initially, but if you keep increasing your parameter, this is the viscosity, then you see flow passes through another critical point which resides very far away from the horizon, somewhere here. Horizon is somewhere here. Okay, so in accretion flow, as explained earlier also, the accretion flow dynamics has to be transonic, because here is flow is subsonic, here is it has to be supersonic. So it might have a inner critical point, it might have a two inner critical point by which flow might pass supersonically, and this may dictate by the viscosity. Okay, so moving on. So once flow becomes supersonic, and as I said, there is a centrifugal barrier. Okay, so sometimes what happens is, let's say for a general consideration, let's say if there is a people which are doing skiing and they are moving with the greater than the speed of the sound. So if their hurdle comes up, they are no longer to communicate with each other. Like they can't tell if there is a hurdle or there is a wall. So what will happen? There will be a pile up of matter or density will go down drastically, and there might be existence of shock given by Rankine-Revelwood condition, which is nothing. Conservation of mass, this is the accretion rate. This is conservation of energy, which is a local energy, which is sum of kinetic, thermal, and potential energy, and this is the momentum. Okay, so let's see now. So let's since flow is going, flow pass through the outer critical point, becomes supersonic. Then we use these RSC conditions to see if there is a shock or not. If RSC condition is satisfied in the flow, then you got a shock transition, and flow move to the subsonic branch, and again plunge into the black hole by passing through the inner critical point. And this might be true for non-rotating black hole and also for maximally rotating black hole. Okay. So yeah, as there is a shock, so other flow variables will also get shocked. So this is a density, this is a discrete transition, this is temperature, this is, and interestingly, this is the this entropy accretion rate. And here, as you can see, at this shock transition, the entropy is increased. So this transition is also followed by the second law of thermodynamics. And this is the interesting. If you see, this is a simple to cooling. You can see this is the arc centimeter cube per second. You can see here how much amount of energy we can extract. This is a very large amount. Okay, so this can be true for AK0 and 0.90. And let's see how this shock solution might behave with the change in the theta. Okay, so here as I said, there might be shock, there might not be shock, depending on the flow variables. So here, flow was here, so we tried increasing the viscosity, and we see as we increase the viscosity, more magnetic motor has been removed. So it's like the barrier which is given by the centrifugal barrier is become weakened. So now gravity wins and shock goes inward. And but you can't have a shock for every flow variable. But if you keep increasing the velocity, centrifugal barrier weakens this much, so it supports no shock. So after a critical value, there is no shock in the flow. So depending on the flow variables, this accretion flow might induce shock or might not. So this depends on the flow variable that we choose on outer edge from where we are injecting the parameter, or even what we are changing. Okay, so next if we increase the theta, what happens to other shock variables? So here this is the shock location, as I explained. As we increase the theta, shock goes inward, and this is the compression ratio. So as shock location goes inward, the shock gets compressed more and more, and so from there you can extract more energy from the shock. Okay, so yeah, and this is the shock strength. This is the ratio of the Mach number to Mach number at the upper branch and the lower branch. So this is similar to compression ratio, and this case might be true for AK0 and 0.90. And other things here we do is we increase the cooling. So here in case of alpha naught or theta, it was a centrifugal barrier, but there is another barrier which is the pressure, which is isotropic. So if we increase the cooling in the system, the pressure has been decreased. So now the less barrier is given by the pressure. So in this case also, as we increase the cooling, shock will go inward as for other variables. Okay. So as I said, this flow might have shock or might not have. So to be sure that there is shock, we plot a region which we call a shock parameter space, which dictates around under this region. If we choose these values, we will definitely have a shock. Okay. So as we increase here theta, means we are increasing the dissipation. As we increase dissipation, system getting more damped and damped. Okay, so after a point, you don't get any shock. It's just shrinking. Parameter space is shrinking. So after a point, if you increase further from these values, the shock will disappear. Okay, and this might be true for 0, here for 0 and 0.9. Yes, and another thing is we do is how we also change, if we change the spin of the black hole. If we change the spin of the black hole, this how shock may behave. So if you see this potential, here there is a coupling term between the spin and the flow angular momentum. So if you are increasing the AK, you are supporting the angular momentum. So if you then the centrifugal gets more stronger, so it will push the shock outward. So as you can see, if we are increasing AK, the shock location is increasing outward. So yes, and theta I have explained you. So let's say for a given AK, if you choose higher theta, shock location will go inward. And interestingly, as I told you, now we have two parameters for viscosity. So one has been intrigued what is their relation. So here we try to see what is their relation between alpha naught and theta if there is a shock. Only if there is a shock, because shock has its own importance. Okay, so here you can see the relation between these theta max, and theta max is the value where after which we don't get a shock for a particular value of alpha. Okay, so moving on. Next, as earlier told by Professor Shantiputra Das, SOAC has its importance to determine the frequency of the quasi-periodic oscillation. And what is quasi-periodic oscillation? And let's say we have this source. I have this source. Like if we get it, turn it on and off after every 5 seconds. And if you plot a slide curve, there will be like after 5 seconds there is a peak. But it doesn't come after 5 seconds. You do 4 or 3. So you don't get a sharp peak, but you get a extended peak. I mean, if you take it the Fourier transform, you will have if it's periodic, you get a delta function. But if it's not purely periodic, it has a width. So that we call it quasi-periodic. If there is a quasi-periodic behavior in the outburst activity of the any source. And earlier it's been explained said that after a shock, this get puffed up due to the temperature, high temperature, and can take this symbol, we call it a symbol of post-shock corona. And if it oscillates, or there is any resonance, it might give us those PPO, and which is rated by in-fault time scale. And in-fault time scale is rated to the where is your shock. See, this is the shock. Okay, we integrate this from shock location to the price area. So if your shock is near to the black hole, you get a higher QPO. Okay. So this is all from my side. So here what we had did, we consider a viscosity distribution and showed how the dynamics is governed by this viscosity parameter. We also showed that shock-induced solution is harbored by the accretion flow, and we also showed what is the correlation between these two viscosity coefficients. I also showed how this QPO frequency might vary with theta. So yes, thank you all.
Okay, thank you for your nice and informative presentation. It's now open for discussion.
Yes.
The bounds on theta that you put, I mean, theta specific theta values you chose.
Here?
Yeah, those theta values.
Yes.
And from earlier cases also you have chosen some specific set of theta values, no?
Yes.
So, under what motivation you have chosen that specific bound only?
See, it depends upon the what flow variables basically you have. Suppose let's go here. Let's say here. Let's go here. If where I choose my flow from where I am injecting the matter. So I can inject matter from here also. I can inject the matter from here. So let's suppose you choose your this theta value here. So what will it will do? When you set the theta alpha naught, you have set the transporter value. So if you set here, it will the amount of transport amount of angular it will transport will be lesser than the here. So it just all depends on where you are choosing your this injecting radius and what is your lambda there basically angular momentum. So it might vary. So here that's what we wanted to show here. Here for theta max.
So and these two are basically for that specific bound of theta.
Yes, for a particular value of alpha naught, we get this value of that so that we can have a shock.
So you are trying to constrain the bounds of alpha using that theta also.
There is not particularly bound on alpha naught, but for a given alpha naught, we can put at least on the theta.
And is there any kind of, in the available literature, I don't understand just asking.
What?
I mean, in the available literature, is there any kind of bounds given on alpha? And
Yes. Recently there was a paper by Narayan et al. For Sagittarius star. They have constrained the value of alpha now.
Yes, there are a few questions. Yes, please go ahead, one by one.
Can you go to that slide number 15?
Slide number 15. Okay. Sorry. Yes.
Just help me understanding this graph. The point there marks some R suffix, that is the point for this side, on the right hand side. That is the point for the critical point for super.
After that, the flow becomes supersonic.
And the on the right hand left hand side, that is for subsonic, right?
Yeah, from here, flow jumps from subsonic to supersonic, or here also flows jumps from subsonic to supersonic.
Okay, just after for between values of theta, just after it crosses the supersonic point, when R suffix, there is a sharp transition. It goes up and then there is a sharp transition. Why is that? Could you explain that?
Because that is basically a shock location.
Oh, that exactly that sharp location.
Yes, that is a shock location where this shock transition happens basically.
Okay. Okay, and that corresponds to different R, right?
Yeah, that corresponds to different theta value. We have different shock location.
Okay.
Yeah, yeah.
So can you move to that slide number 9?
Slide number 9.
Yeah.
Yeah.
So maybe not this one. There was a potential, effective potential.
Okay, yeah, sure. It's this one.
Sorry. So in that one, that means this is the effective potential that we are going to encounter on that accretion region.
No, this is the potential which we use for a black hole. It also have a potential.
Okay.
Like if you have a cliff.
Yes.
From cliff,
Yeah.
you took matter from there to some height edge.
So now that means this effective potential is going to affected by the viscosity of that accretion.
No. This is not affected by the viscosity. But yeah, this might also viscosity because lambda is sitting there.
Yeah, lambda is sitting there. So you now just say that they have given bounds on those parameters near series A star for that theta.
But this potential might be different.
Yeah, potential.
Might be different because maybe they have considered because that is a supermassive black hole basically.
Yeah.
So they are considering the outer region. So I guess there is a pseudo Newtonian or something like that there. I guess.
Okay, so in that case, like just like you said, there is the dependence of this lambda parameter here. So if there are matter in that region, even in case of supermassive black holes, so that effective potential should get affected by.
Yeah. If you plot this phi effective, it will change, but the change that you will see that may be minor. But there will be a change with changing the theta or changing the lambda.
So that actually depends on how active the black hole is. I mean, like
How much it is actually.
yeah, how much it is active in the matter.
AK is there because this if you see the AK and lambda also is there.
Yes.
So it also defines it's a prograde or retrograde.
Yeah. I can get that.
Okay.
Thank you.
Any more?
Is there any more questions? So I am interested in knowing the physical basis of choosing this scaling law of viscosity.
As I said, in the literature, it has been shown in this GRMC literature.
Before that, just alpha as a function of that.
This was noted by these studies where they have shown this alpha might vary up to about 0.5. So because a different system might behave differently depending on the mass and the speed. So to be a more generalized case, we have chosen it to be power of some theta.
Okay, and as it was already mentioned, so your spectral index theta, how do you choose from case to case?
Case to case, as I said, told to him is depend on from where you are injecting the matter.
Okay. And what is the effect of this on MRI?
MRI, that I didn't study, so I can't comment on that, I guess.
Okay, thank you. So let us thank the speaker once more. Now, next speaker, Peter Liang Thang, and the topic is understanding of Saturn's internal magnetic field from the Pioneer 11 to the Cassini.
Morning, everyone. This paper was the outcome of the study of a charged particle, where we were studying the charge dynamics in the certain rings. We realized that this magnetic field, about the information about the magnetic field itself is blurred. There is no proper literature on what the magnetic field is, how does it look like, all those. And then as we go deeper, we realized that there is no literature on certain magnetic field, proper literature. And there are so many models on the magnetic field that we don't know what to choose. And a part of the literature review, we thought, okay, this is enough information, or let's say a kind of handbook of magnetic field. We would like to make a kind of handbook or reference on the certain magnetic field. This is a outcome. So there will not be much of the theoretical discussion like how the models are made, what techniques are used. Rather, we would like to present this paper in the form of what we call a handbook reference paper on certain rings, so that any other who is interested to study the certain, the charge dynamics or the certain rings itself with what we call the effects of non-gravitational force like plasma drag, all those, they can use this book, or rather this paper, for their studies. So this is, in a sense, a review paper which systematically will give analyze of the magnetic field, what it is, all those, and then what are the shortcomings, all those. So let me move ahead. Our motivation, as I said, is to have a clear knowledge and understanding of certain intermagnetic field and use it in the studies of non-gravitational force. Here by non-gravitational force, we mean electromagnetic effect, plasma drag, atmospheric drag. All those we need the knowledge of magnetic field. Then this magnetic field itself can tell many information about the object of the studies. Even if we say we are studying the black hole, if we can have knowledge about the magnetic field created by the black hole, I think we can understand what is inside. So this magnetic field is like a probe of any object. Therefore, we thought that if we have a proper understanding of this magnetic field, we will have a clear understanding of certain internal, not only that, then how the rings are formed, how the rings behave, all those, which will surely be affected by the magnetic field. So that is the significance of this paper. Sorry. The exploration and observation of models of certain internal magnetic, it started, this magnetic field of Saturn was discovered by the pioneer 1979. What are the things which it discovered? Of course, discovered in the sense it detected, but once it detected, there was no how does just detecting magnetic field does not mean that we exactly know how it is. Is it a dipole? Is it a quadrupole? So we we need to analyze those data and then come up with a model. Based on those models, these are the things which the characteristic of this planet magnetic field, which is known today. It is highly symmetric about the rotation axis, symmetric in the sense of left, right in the coordinate system. Then it has dipole moment, then it is offset. Here, by offset we mean, we consider the magnetic field to be created by a dipole, and that dipole, the center of dipole, does not coincide with the center of the planet. That is the meaning of offset. That is a little bit above the center of the planet. Then has a polarity opposite to that of Earth. That means the north becomes the north pole of the magnetic field. Then the tilt, the magnetic axis, the rotation, the axis between the rotation and the axis between the magnetic field is found to be almost perfectly parallel to each other. This becomes the hot topic for later on. Then later on, in 1980, Voyager was sent, but this Voyager spacecraft again substantiated whatever the findings of the Pioneer 11. but a little bit different of the calculation of the dipole moment and the tilt now, which was given to be less than 1 degree. Okay.